Since 2005, AguaClara has been working to provide clean water on tap to communities across the world. As of 2020, our gravity-powered water treatment plants provide drinking water to over 83,000 people in Honduras, Nicaragua, and India. Water treatment is important for community health because it removes organic matter, dirt particles, and pathogens, which can cause life-threatening diseases. In this video, we will show how AguaClara plants work by going over the four main treatment processes: coagulation and flocculation, sedimentation, filtration, and chlorination. Let's get started. Welcome to Gracias Limpera, Honduras. This 120 liter per second plant is designed to provide over 20,000 people with safe drinking water on tap. We'll be using Gracias as an example of how water flows through an AguaClara plant. Let's go inside. We're standing on an elevated platform inside the plant where you can see all of the water treatment processes. The plant is split into two treatment trains, meaning that water can travel through either the left or the right side of the plant. Since the plant is powered by gravity, a nearby stream or river that is higher in elevation serves as the water source. Water enters the plant through an influent pipe in the entrance tank. Influent refers to water flowing into a tank or channel, while effluent refers to water flowing out. After the entrance tank, the water flows to the flocculator, where it is dosed with a sticky chemical called coagulant. The purpose of flocculation is to force particles to collide and stick together to form clusters called flocks. These flocks settle out of the water in the sedimentation tank. After the majority of particles have been removed, the water is typically sent through a stacked rapid sand filter to capture the smallest particles that escape sedimentation. Finally, before water is released to the community storage tank or distribution system, chlorine is added to deactivate any pathogens that remain in the water. To reiterate, the chemicals used in an AguaClara plant include coagulant used for flocculation and chlorine used as a disinfectant. The chemicals are stored in large containers on the elevated platform. Coagulant flows by gravity through pipes and flexible tubing to the entrance tank, while chlorine is added at the end of the treatment process. This system of tubing is part of the chemical dose controller, which is found in the entrance tank. The entrance tank consists of an influent pipe where water enters the plant, a trash rack, a linear flow orifice meter abbreviated as LFOM, and components of the chemical dose controller called the CDC for short. The trash rack is a grate that catches large debris, such as leaves, to prevent blockages. The trash rack also dissipates some of the water's kinetic energy, helping to keep the floating component of the CDC in place. The water exits the entrance tank through the LFOM, which consists of a pipe with rows of holes drilled into it. Its geometry ensures that the height of the water in the entrance tank is proportional to the flow rate through the plant. This helps maintain a constant chemical concentration as the flow rate through the plant changes. The plant operator can quickly approximate the flow rate by counting the number of rows that are submerged in water and consulting a chart. The diameter of the LFOM pipe depends on the capacity of the plant. Part of the chemical dose controller system is located in the entrance tank. It automatically adjusts the amount of coagulant and chlorine added to the water based on the current flow rate into the plant. The tubing that transports the chemicals is attached to a lever arm whose angle is controlled by a float on the surface of the water. Rotating the lever changes the vertical distance between the constant head tank and the drop tube. This height difference drives the potential energy of the chemicals. In summary, when the flow rate changes, the lever rotates, and the chemical flow rate adjusts accordingly to maintain a constant chemical dose. The plant operator can make manual adjustments to the chemical dose by sliding the drop tube up or down the lever arm. For example, when a heavy rain event increases the turbidity of the water, the operator typically adjusts the tubing on the CDC such that the height difference between the drop tube and the constant head tank is larger, thus increasing the flow rate and dose of the chemicals. Flocculation is the process in which particles collide and stick together to form snowflake-like fractals called flocks. Flocks are easier to remove from the water than individual particles because they have larger diameters and therefore settle faster in the sedimentation tank. To facilitate flocculation, a sticky substance called a coagulant is added to the water. Coagulant nanoparticles coat the surface of particles and act like glue. The most common coagulant used in AguaClara plants is polyaluminum chloride, also known as PAC. The coagulant dose is determined by the chemical dose controller, as previously mentioned. The flocculator consists of a concrete channel segmented by large plastic sheets called baffles. The baffles are staggered across the top and the bottom of the flocculator, forcing the water to flow in a vertical zigzag pattern. The baffles in the flocculator create fluid deformations by repeatedly forcing the flow of the water to change directions. These fluid deformations cause particles to collide, and their coagulant coating sticks them together to form flocks. Pieces of pipe attached between the baffles creates additional fluid deformation by obstructing the flow of water. The flocks travel to the end of the flocculator, where they enter the influent channel of the sedimentation tank. In sedimentation, flocks settle towards the bottom of the tank, leaving cleaner water at the top. The influent channel distributes water evenly to each sedimentation tank through a series of holes on the bottom called orifices. The influent manifold directs this water to the bottom of the sedimentation tank through a line of semi-flattened pipe stubs called diffusers. Upon entering the sedimentation tank, the direction of water flow is immediately reversed from downwards to upwards. This upward velocity resuspends any flocks that were settling at the bottom of the sedimentation tank. The suspended flocks form a constantly moving bed of particles called a flock blanket. The presence of a flock blanket is one of the aspects that makes AguaClara plants unique. Particles in the water can get caught in the flock blanket, contributing to the high particle removal efficiency of AguaClara sedimentation technology. The bottom geometry of the sedimentation tank is extremely important to its function. Notice that the diffusers are slightly offset from the center of the jet reverser and that the sides of the tank are sloped. Experiments demonstrate that these design choices are required for a flock blanket to form. The diffuser geometry distributes water evenly across the tank and ensures that water only flows in the vertical direction. Horizontal velocity components decrease particle removal efficiency because they create large-scale circulation which carries flocks upwards with the clean water. Additionally, the sedimentation tank is designed with minimal horizontal surfaces where flocks can accumulate without recirculation. When flocks stop moving, they form a thick layer of sludge which can become anaerobic and produce methane. In addition to producing foul odors, the methane gas bubbles decrease the efficiency of the sedimentation tank by carrying flocks to the surface of the water. Another issue is that settled flocks can clog the diffusers on the influent manifold. Eventually, excess particles need to be removed from the sedimentation tank as the flock blanket grows in density and height. This cleaning process happens automatically when the flock blanket reaches the height of a wall in the sedimentation tank, called the flock weir, and flocks spill into an adjacent tank called the flock hopper. The plant operator manually opens the valve to allow the concentrated sediment and mud in the flock hopper to exit the plant. Since this waste is mostly made up of particles present in the raw water, it can be deposited back into the environment safely. The flock hopper is typically drained 2 to 3 times per day. As water moves upwards in the sedimentation tank, it passes through plate settlers, which are evenly spaced sheets of plastic, designed to capture any particles that were missed by the flock blanket. Gravity causes these particles to settle onto the slanted plates. As the layer of particles builds up, they combine to form larger flocks which slide off of the plate settler and recombine with the flock blanket below. Plate settlers are introduced in the AguaClara design because their geometry increases the total surface area available for settling while occupying a compact space. The geometry of the plate settlers is balanced with the upflow velocity of the water to remove as many particles as possible. Clean water leaves the sedimentation tank through the effluent manifold, which is positioned slightly below the water surface. This is done for the ease of construction and to prevent floating particles from traveling out of the tank with the clean water. This floating scum may contain small flocks that escaped capture and foam created by dissolved organics in the water. Plant operators prevent large buildups of scum by occasionally skimming the surface of the water. The flocculation and sedimentation processes remove the majority of the particles and pathogens present in the raw water. The purpose of filtration is to capture the smallest particles and flocks that were not captured by the flock blanket and plate settlers. AguaClara plants utilized stacked rapid sand filters, which were invented by AguaClara in 2010. The main advantage of the STARS filters is that they are highly space efficient and do not require a pump for cleaning. However, in some plants, the water exiting the sedimentation tank already meets quality standards, so filters may not be required. The water travels from the sedimentation tank to the filters through 4 influent pipes. A lever allows the plant operator to divert water from one filter to another, which is useful for cleaning purposes when the water availability is low. Additionally, the filter can be bypassed or turned off entirely by plugging the influent tubes with pipe stubs. The STARS filter consists of a tall cement box filled with sand, which is divided into 6 layers by alternating grids of influent and effluent pipes. The round holes on the influent tubes allow water to enter the filter. In contrast, the slits on the effluent tubes allow clean water to exit but prevent sand from also leaving the filter. Due to the alternate stacking of the influent and effluent pipes, the water can travel both up and down through the layers of sand, and out through the effluent tubes. As water travels through the filter, particles build up constrictions, which are narrow channels between the sand particles. This particle buildup forces the streamline of water closer together, making it more likely for particles to collide and attach to the sand. Therefore, a filter is actually better at removing particles when it is slightly dirty. By conservation of mass, the velocity of water through the constrictions must increase as the channel narrows. Eventually, the velocity of water is so high that its shear force prevents new particles from attaching to the sand grains. In this state, the constriction is considered to be clogged because it can no longer capture particles. A particle can continue through the filter until it reaches a region of sand with less buildup in the constrictions. A spike in the effluent turbidity is an indication that the entire filter is clogged. The filter needs to be cleaned before this failure mode is reached. We call this process backwashing the filter. Backwash is accomplished by plugging the top 3 influent pipes and sending water upwards through only the bottom influent pipe at the fluidization velocity, which is 11 millimeters per second for AguaClara filters. At this velocity, the downward pull of gravity on the sand is balanced by the upward flow of water, causing the sand to behave like a fluid. This movement of sand knocks particles free from the sand, causing dirt to rise to the surface of the filter. A siphon sucks away and discards dirty water from the top of the filter. The filter is typically backwashed for about 15 minutes until the water starts to clear up at the top of the filter. The plant operator decides to backwash when the head loss between the influent filter box and the effluent filter box is higher than normal. This head loss is determined by comparing the height of water in each box. Chlorine is a disinfectant that is added to the water after all other unit processes to destroy any remaining pathogens. Waiting to chlorinate until after the sedimentation and filtration processes are complete is important, because then the quantities of particles and dissolved organics are as low as possible. Chlorine can react with organic matter to form disinfection byproducts such as carcinogenic trihalomethanes. Additionally, higher doses of chlorine are needed to reach and kill pathogens that are embedded in large particles. Therefore, it is safer and more efficient to remove as many particles from the raw water as possible before chlorination occurs. The chlorine dose is large enough to kill the pathogens that remain and small enough that it is mostly reacted or dissipated by the time that it arrives at the point of use in the community. The processes of coagulation and flocculation, sedimentation, filtration, and chlorination are simple yet powerful in producing drinkable water. Each plant is truly unique, with every AguaClara community contributing its own resources, creative solutions, and a passion for providing clean water for all. To learn more about AguaClara technology, check out the AguaClara textbook, review our research on GitHub, or visit us online on our website. Thank you for watching.